Hello everyone. My name is Dr.E.Purushotham, Associate Professor of Physics, Department of Physics, School of Sciences and Humanities. Today, I am going to discuss about optical fiber or fiber optics. What is optical fiber or fiber optics? So, optical fibers are made up of glass or plastic. These are so designed to guide the information carrying light waves for the proper guiding of information carrying light waves we need a proper guiding medium or material. This type of material is called optical fiber or fiber optics. Optical fiber or fiber optics, what I am saying, the optical fibers are made up of glass or plastic. These cylindrical tubes, the glass or plastic cylindrical tubes, so designed to guide the information carrying light waves using the total internal reflection phenomena. For the proper guiding of information carrying light waves, we need a proper guiding medium or material. This type of material is known as optical fiber. So you see here, an optical fiber is a cylindrical waveguide made up of transparent dielectric material, that is glass or a clear plastic. Already I told optical fibers are made up of glass or plastic, which guides the light waves along its length by total internal reflection. This is the working principle of optical fiber, total internal reflection. Total internal reflection. It is as a thin as human hair, approximately 70 micrometer. The thin of human hair is approximately 70 micrometer or 0.003 inch diameter. So here you note that a thin strand of a metal is called a wire or a thin. So optical fibers are made up of glass or plastic. Cylindrical tubes designed to guide information carrying light waves using the total internal reflection for the proper guiding of information carrying light waves. We need a proper guiding medium or material. That material is known as optical fiber. Optical fiber. So you see here in this, the optical fiber light signal is passing through this fiber cable. This is the fiber cable. The innermost region, this is core, this is cladding. So the light signal enters into the core medium. It is moving like this. So optical fiber is a technology in which signals are converted from electrical into optical signal, transmitted through a thin glass fiber and reconverted into electrical signals. What I am saying here, optical fiber or fiber optics is a technology in which signals are converted from electrical into optical signals, transmitted through a thin glass fiber and reconverted into electrical signal. The optical fibers are made up of glass or plastic. These are having the innermost region, core, and cladding. The optical fiber working principle is total internal reflection. What is total internal reflection? We will go to study in this video. Okay, so you can see clearly the light is propagating through the optical fiber. The optical fibers are made up of glass or plastic. These are so designed cylindrical tubes to guide the information carrying through the light waves using the total internal reflection from one end to another end. So you can see here the working principle of optical fiber. The propagation of light in optical fiber from one of its end to the other end is based on the principle of total internal reflection. Total internal reflection. So in this optical fiber, just you try to understand this is the optical axis. Optical axis. So the light ray enters into the core medium. The light ray enters into the incident angle I. It refracts into the core medium. Then the light gets the total internal reflection and travels from one end to another end. That is the working principle of optical fiber. Optical fiber. The propagation of light or the propagation of light signals from one end to another end, they are you moving with the total internal reflection phenomena. What is the principle? The propagation of light in an optical fiber from one end of its ends to the other end is based on the principle of total internal reflection. Simply, the light signal passing through the optical fiber using the total internal reflection from one end to another end. From one end to another end. This is the working principle of optical fiber. So you can see here principle and construction of optical fiber. You see here what is the definition. When the light ray travels from denser medium to rarer medium. So you see this is the normal, this is the surface. I am taking surface as S, normal N. We can also here this is the denser medium. This is the denser medium. You can see here denser medium. This is the rarer medium. And also we can also take here reverse. What happened? We can see both are same. Denser medium. This is rarer medium. So this is refractive index of denser N1, refractive index of core N2. N1 should be greater than N2. So here this is denser N1, rarer N2. N1 should be greater than N2. When the light rays travels from denser medium to rarer medium. Here also we can see here the light rays enters into the denser medium to rarer medium. It refracts into the rarer medium with refraction angle smaller. Here also you can see this is the refraction angle smaller. You see here clearly when the light ray travels from denser medium to rarer medium. The light ray travels from denser medium to rarer medium. Denser to rarer medium. You see, the refracted ray bends away from the normal. When the angle of incidence is greater than the critical angle, the refracted ray again reflects into the same medium. This phenomena is called total internal reflection. So here, what I am saying here, so this is a normal, this is surface. When the light ray is incident with the incident angle I, so it refracts into the rarer medium. This is a denser medium. The light ray travels from denser medium to rarer medium. The light ray is incident on the surface with incident angle I, then the refraction angle smaller. It refracts into the rarer medium with the refraction angle. I value increases, the refraction angle also increases. Refraction angle also increases. Refraction angle also increases. At a particular incident angle, at a particular incident angle, the refraction angle, the refraction ray travels along the surface, then the angle is 90 degrees. From here to here, the angle is 90 degrees. 90 degrees. Then that angle is called critical angle. Critical angle. If the incident angle is greater than critical angle, the light ray enters into the same medium, reflects into the same medium, that is called total internal reflection. At the definition, just finally we will discuss about the definition. Just to try to understand the definition. What I am saying here, when the light ray travels from denser medium to rarer medium, the refracted ray bends away from the normal. You see here. So the refracted ray bends away from the normal. When the angle of incidence is greater than the critical angle, the refracted ray again reflects into the same medium, that is called total internal reflection. So simply, I am giving here total internal reflection definition. This is normal. This is surface. This is denser medium N1. This is rarer medium N2. The light ray travels from denser medium to rarer medium. With the incident angle is greater than critical angle, then the incident total light ray reflects into the same medium, that is called total internal reflection. That is called total internal reflection. Okay, we can see here, we can see here, okay, before going to discussion about I is less than theta c, I want to discuss Snell's law. What is Snell's law? What is Snell's law? Let us consider, you see here, this is the denser medium N1, this is rarer medium N2. Let us consider N1 and N2 are the refractive indices of denser and rarer media respectively. What I am saying, let us consider N1 and N2 are the refractive indices of denser and rarer media respectively. Then Snell's law, according to the Snell's law, the ratio of sin I to the sin R for a given pair of media remains constant. That is equal to constant. That constant is equal to refractive index mu r n. Refractive index mu r n. So sin I by sin r is equal to n2 by n1. N2 by n1. Why we are taking mu is inversely proportional to sin I? So sin I by sin r is equal to n2 by n1. So we can write n1 sin I is equal to n2 sin r. It is known as Snell's law. Snell's law. The ratio between sine of incident angle to the sine of refraction angle is equal to constant. That constant is equal to refractive index is called Snell's law. Or n1 sin I is equal to n2 sin r. That is Snell's law. Snell's law. You need to remember what is Snell's law. Snell's law. So this is denser medium refractive index N1, rarer medium refractive index N2. N1 should be greater than N2. Therefore, Snell's law definition, you see here, sine of incident angle to the ratio between sine of incident angle to the sine of refraction angle is equal to constant. That is equal to refractive index mu or n. So sin I by sin r is equal to, so we can take refractive index 1 to 2. The light ray travels from n1 to n2. So sin I by sin r is equal to n2 by n1. So we can write this is n1 sin I is equal to n2 sin r. This equation is known as Snell's law. Snell's law. So okay, first condition, case 1, I less than critical angle. The light ray refracts into the cladding medium. This is figure 1, cladding medium. So let a light ray move from denser medium to rarer medium. Always I am telling this is a denser, this is rarer. The light ray travels from denser medium to rarer medium. Let a light ray move from denser medium to rarer medium with incident angle I and refraction angle small r. Incident angle I, so refraction angle smaller. Then, according to Snell's law, according to Snell's law, N1 sin I is equal to N2 sin R. N2 sin R. Okay, case 2. If I is equal to theta C, I is equal to theta C. So this is a denser N1. This is a rarer medium N2. Here also N1 should be greater than N2. The light ray travels from denser medium to rarer medium. If I is equal to critical angle, the light ray travels along the interface and cladding. Theta C is known as the critical angle. What I am saying here, clearly try to understand. When I is less than theta C, then the light ray simply refract into the second medium we discussed. But when I is equal to theta C, I is equal to theta C, try to understand. The refracted ray simply coincide with the interface or surface. What I am saying here, the incident angle is equal to critical angle. The refracted ray travels along the surface. So from this surface to this normal, the refraction angle is equal to 90 degrees. Refraction angle is equal to 90 degrees. So we can calculate the critical angle. When the angle of incidence is increased, angle of refraction also increases. And for a particular angle of incident, I is equal to theta C, the refracted ray travels along the interface of the two medium. This angle of incident is known as a critical angle. What I am saying clearly, try to understand here. If the light ray is incident, I is less than theta c, so this is the refraction angle. The incident angle increases, refraction angle also increases. At a particular incident angle, at a particular incident angle, the light ray travels along the surface. That particular angle is called critical angle. Particular angle is called critical angle. When the angle of incidence increases, what I am saying, the angle of incidence I increases, refraction angle also increases. At a particular incident angle I is equal to theta c, the refraction angle gets 90 degrees. Then the incident angle is called critical angle. I is equal to theta c. So according to Snell's law, what is the Snell's law? You try to understand here. Snell's law. I am applying here Snell's law. N1 sin I is equal to N2 sin R. But I is equal to theta c, R is equal to 90 degrees. Just substitute in Snell's law. So N1 sin theta c, at the place of I am substituting theta c. N2 sin 90 degrees. What about sin 90? N1 sin theta c is equal to N2 into 1, sin 91. So sin theta c is equal to N2 by N1. You can see here sin theta c is equal to N2 by N1. Therefore, theta c is equal to, we can write sin inverse of N2 by N1. This angle is known as critical angle. This angle is known as critical angle. Okay, again you try to understand critical angle. Snell's law. According to Snell's law, I am taking here, according to Snell's law, N1 sin I is equal to N2 sin R. But incident angle I is equal to critical angle theta c, you can see here. So refraction angle R is equal to 90 degrees. Substituting in above equation, N1 sin theta c is equal to N2 sin 90 degrees. So N1 sin theta c is equal to N2 into 1. So we can write here, what is this? Sin theta c is equal to N2 by N1. This N2 by N1. What about theta c? Sin inverse of N2 by N1. This angle is known as critical angle. Critical angle. What is critical angle? When the angle of incidence is increases, the angle of refraction also increases. And for a particular angle of incidence, at a particular angle of incidence, the refracted ray travels along the interface of two mediums. This angle of incidence is known as critical angle. Critical angle. Okay, next. Case 3. When I is greater than, you see here, incident angle is greater than critical angle, then the light ray will be reflected back into the same medium or core medium and undergoes total internal reflection. That is called total internal reflection. What I am saying here, so this is a denser medium, this is a rarer medium. So the incident angle I increases, the refraction angle also increases. At a particular incidence angle I is equal to theta c, the light ray travels along the surface. That angle is called critical angle, then R is equal to 90 degrees. And also increases incident angle, the light ray reflects into the same medium. That phenomena is called total internal reflection. This phenomena is called total internal reflection. What I am saying, when the incidence angle value increases, refraction angle value also increases. At a particular incidence angle, I is equal to theta c, the light ray travels along the surface, then also increases incidence angle, then the light ray reflects into the same medium. Phenomena is called total internal reflection. When the angle of incidence is greater than the critical angle, the refracted ray again reflects into the same medium. This phenomena is called total internal reflection. So, what I am saying here, when the angle of incidence I is greater than the critical angle, the refracted ray again reflects into the same medium. Phenomena is called total internal reflection. So, what is the working principle of laser? We discussed here principle and construction of optical fiber. Definition you can see clearly, you can understand now. When the light ray travels from denser medium to rarer medium, the refracted ray bends back from the normal. When the angle of incidence is greater than the critical angle, the refracted ray again reflects into the same medium. This phenomena is called total internal reflection. What I am saying here, clearly try to understand. Incidence angle is increases, refraction angle also increases. At a particular angle, I is equal to theta c, that is critical angle. The refraction angle gets 90 degrees. Then the light ray travels along the surface. Then also incidence angle increases above the critical angle. Then the light ray reflects into the same medium. This phenomena is called total internal reflection. That is the working principle of optical fiber. When the light ray incident with the incidence angle I, the incidence angle I value increases, refraction angle also increases. At a particular incidence angle I is equal to theta c, the light ray travels along the surface, then refraction angle gets 90 degrees. Then also I is equal to theta c. Above theta c, the incident angle value increases. Above theta c means I is greater than theta c. Then the light ray reflects into the same medium. Phenomena is called total internal reflection. That is called total internal reflection. So let us consider N1 and N2. Where is N1? This is N1, denser medium. This is N2, rarer medium. Let us consider N1 and N2 are the refractive indices of core and cladding medium. Let a light ray travels from denser medium to rarer medium or core medium to cladding medium. So this is a denser core. It behaves as cladding. Cladding. Okay. Let us consider N1 and N2 are the refractive indices of denser and rarer medium, or refractive indices of core and cladding mediums. Let a light ray travels from core medium to cladding medium or denser medium to rarer medium. Then the refracted ray bends away from the normal, with I is the angle of incidence and I is the angle of incidence, R is the angle of refraction. So in this we get three cases. One is I less than theta c. This is the first case. I is equal to theta c. This is the second case. I is greater than theta c. This is the third case. So we are discussing first case, case 1. I is less than theta c. The light ray reflects into the cladding medium. So what I am saying here, according to Snell's law, we can also write N1 sin I is equal to N2 sin R. Let us consider N1 and N2 are the refractive indices of denser and rarer medium, respectively. A light ray move denser to rarer medium with incidence angle I and refraction angle R. If I is less than theta c, the light ray refracts into the cladding or rarer medium. Rarer medium. That is first case. So second case. Second case, I is equal to theta c, critical angle. So incidence angle value increases, refraction angle value also increases at a particular angle, critical angle, the refraction angle is 90 degrees. So you see here, when the angle of incidence increased, angle of refraction also increases. And for a particular angle of incidence at I is equal to theta c, the refracted ray travels along the interface of two mediums. So the light ray travels along the surface. So between this surface and normal incidence, R is equal to 90 degrees. R is equal to 90 degrees. So I am applying the Snell's law. N1 sin I is equal to N2 sin R. N1, what about sin I value? I is equal to theta c. What about R value? 90 degrees, sin 90 degrees, sin 91. So sin theta c. This is N1 as it is. N2 into sin 91. So sin theta c is equal to N2 by N1. Theta c is equal to, you can get sin inverse of N2 by N1. Sin inverse of N2 by N1. So you can see here when I is greater than critical angle. Already we discussed here, incidence angle value increases, refraction angle value also increases. At a particular angle, critical angle, the refraction angle gets 90 degrees. So above the critical angle, the light ray reflects into the same medium. Phenomena is called total internal reflection. Total internal reflection. When the angle of incidence is greater than the critical angle, the refracted ray again reflects into the same medium. This phenomena is called total internal reflection. This total internal reflection is the working principle of optical fiber. You see here, when I is less than theta c, then the ray refracts into the secondary medium, either cladding or rarer medium. When I is equal to theta c, the ray travels along the interface or surface. When I is greater than theta c, then the ray totally reflects back into the same medium. That is called total internal reflection. Total internal reflection. Total internal reflection. Okay, we can take a simple problem on critical angle. On critical angle. So, for example, the refractive indices of core and cladding. So, I am giving a simple problem. The refractive index of denser medium and rarer medium of an optical fiber cladding of an optical fiber 1 point optical fiber or 1.48 and 1.45. Calculate the critical angle. Calculate the critical angle. This is only for your understanding. So refractive index of core 1.48, refractive index of cladding 1.45. So what is the principle? Critical angle is equal to sine inverse of n2 by n1. Simple problem. So refractive index of core 1.48 n1. So refractive index of cladding 1.45, that is refractive index of cladding. Substituting all the values, sine inverse of n2 1.45 by n1 1.48. So we get this is a sine inverse of 0.9797. This is equal to critical angle theta c is equal to 78 degrees 26 minutes. We can calculate the problem. So what I am saying here, the refractive indices of core and cladding of an optical fiber are 1.48 and 1.45. Calculate the critical angle. N1 is equal to 1.48, N2 is equal to 1.45. So critical angle formula sine inverse of N2 by N1, that is equal to sine inverse of substituting the values N2 1.45, N1 1.48. So the critical angle 78 degrees 26 minutes. Conditions to get total internal deflection. What are the conditions to get total internal reflection? The light ray should travel from denser medium to rarer medium, or the light ray should travel from core medium to cladding medium. Core to cladding medium. So second condition, the refractive index of denser should be greater than the refractive index of rarer medium. Number three, we should get the total internal reflection. What is the condition? The incidence angle should be greater than the critical angle. These are the conditions to get total internal reflection. So first condition, the light ray should travel from denser to rarer medium, or the light ray should travel from core medium to cladding medium. The refractive index of core should be greater than the refractive index of cladding. The incidence angle should be greater than the critical angle. These are the conditions to get total internal reflection. So construction of optical fiber. Principle of optical fiber, that is total internal reflection. Already we discussed. When the incident angle is greater than, then the incidence total light ray reflects into the same medium phenomena is called total internal reflection. That is the working principle of optical fiber. So construction of optical fiber. The optical fiber mainly consists of following six parts as shown in this figure. So actually, this is the optical axis. You can see optical axis, optical axis. So this is the core, the innermost region. This is core. It is surrounded by another region, cladding. The cladding surrounded by some coating, that is silicon coating. Around that silicon coating, another jacket is there, that is buffer jacket. Another one, this region, member, strength member. So outermost jacket, this is called sheath or outermost jacket. So the optical fiber consists mainly core, number two, cladding, and number three, outermost jacket, outer jacket. So first you can see here core. A typical glass fiber consists of a central core material. Generally, core diameter is 50 micrometer. The core is surrounded by cladding. The core medium refractive is always greater than the cladding refractive index. So cladding. Second one, cladding. The refractive index is less than the core's refractive index. The overall diameter of the cladding is 125 micrometer to 200 micrometer. Okay, you try to understand the construction of optical fiber. The optical fiber mainly consists of the following six: core, cladding, silicon coating, buffer jacket, strength member, outer jacket, and so on. So already I discussed the core. A typical glass fiber consists of a central core material. The innermost region is called core. The core is made up of glass or plastic. The diameter of core 50 micrometer, 50 micrometer. So the core is surrounded by cladding. So the refractive index of core generally N1 is equal to 1.46. Cladding also made up of glass or plastic. The core is surrounded by another region is called cladding. The overall diameter 125 micrometer to 200 micrometer. So the refractive index of cladding. So here refractive index of core 1.48. This is 1.46. N1 should be greater than N2. Therefore, this behaves as a denser medium. It behaves as a rarer medium. Silicon coating. So silicon coating is provided between buffer jacket and cladding. It improves the quality of transmission of light. What is the use of silicon coating? It improves the quality of transmission of light. Silicon coating is provided between buffer jacket, you see here, between this cladding and buffer jacket. Already you are observing between this one. Okay, this is a silicon coating. Silicon coating is provided between buffer jacket and cladding. It improves the quality of transmission of light. Next, buffer jacket. Buffer jacket. So silicon coating is surrounded by another region, that is buffer jacket. Buffer jacket is made up of plastic and protects the fiber cable from any unnecessary, unwanted, weather related things. So next, strength member. Buffer jacket is surrounded by strength member. It provides strength to the fiber cable. Outer jacket. Finally, the fiber cable is covered by polyurethane outer jacket. Because of this arrangement, fiber cable will not be damaged during the pulling, bending, stretching, and rolling through the fiber cable is made up of glasses. This is the construction. You can see the light ray travels to the optical fiber using the total internal reflection. Simply, that is path of light in core. You can see the path of light in core. You can observe this point to this point to this point. This is core. Okay, you can see the path of light through the optical fiber. The path of light through the optical fiber clearly you can see. So this place to this place, this is the core. Remaining, this is cladding. Cladding. This is core. So simply, we can draw the optical fiber. Very simple. We can see here in another direction also. You can see here. Simply, we can draw it. We can simple. We can also draw here. This is the optical axis. Optical axis. We can also draw here. This is optical axis. Optical axis. So this is core. Core. So this is cladding. So this is plastic jacket or outer jacket. It is also called sheath. It is also called sheath. We can draw like this. So you can see here simply the optical fiber mainly consists of following three parts, main parts: core, cladding, and protective jacket. Protective jacket or sheath. So core, the innermost region which guides the light is called core. Core is generally made up of glass or plastic. The central core of thickness 50 micrometer surrounded by cladding. The refractive index of core is 1.48. The optical fiber mainly consists of three main parts: core, cladding, and sheath. What I'm saying, core, the innermost region is called core. Core generally made up of plastic or glass. The diameter 50 micrometers, refractive index 1.48. So you see here cladding, about the cladding. The core is surrounded by a secondary cylindrical shell or glass called the cladding, which is overall diameter of 125 to 200 micrometer. Already we discussed. The cladding helps to keep the light beam within the core using the phenomena of total internal reflection. So refractive index of cladding is 1.46. The light ray travels. What I am saying here, just you see core, number two, cladding. First point, the innermost region is called core. The core is surrounded by another region that is called cladding. The innermost region is called core. The cladding is surrounded by, the core is surrounded by another region is called cladding. So both made up of glass or plastic, glass or plastic. C. The diameter of core 50 micrometers. The diameter of cladding you can see here 125 micrometer to 200 micrometer. So the refractive index 1.48, refractive index of core. So refractive index of cladding 1.46. So 1.48 is greater than 1.46. So N1 should be greater than N2. This is the condition for total internal reflection. N1 greater than N2. Total internal reflection. So the light ray enters into the core medium. The light ray enters into the core medium and travels from one end to another end with the total internal reflection. Total internal reflection. So, working principle generally, you can see here, this is the, I am giving cross sectional optical fiber. Cross sectional optical fiber. Try to take here cross sectional optical fiber. This is the optical axis, optical axis. The light ray. So I am taking here, this is A, this is B. In an optical fiber, a light ray AB is incident at a point B with an angle theta L is known as launching angle. Launching angle. In an optical fiber, the light ray AB is incident at point B with an angle theta L is known as launching angle. The light ray enters into the core with a certain refraction and strike the interface of core and cladding at point C. At point C. With the angle theta I is greater than critical angle. So it gets a total internal reflection. What I am saying here, with the angle, the light ray refracts into the core medium as BC. It strikes at point C with the incidence angle theta is greater than critical angle. Then the light ray back into the same medium and strike the core cladding interface at point D. At point D also, theta I should be greater than theta C. The incident angle is greater than critical angle. With an angle of incidence greater than the critical angle, again it undergoes total internal reflection. It is incident at point E and D and so on. It travels from one end to another end like E, F, and so on. In this process, the light ray propagate from one end to optical fiber to the other end without loss of energy. Without loss of energy. This is the working of optical fiber. Let us consider a cross-sectional optical fiber. Cross-sectional optical fiber. In an optical fiber, the light ray AB is incident at point B with an launching angle theta L. Light ray enters into core at point B with a certain refraction and strike the interface of core and cladding at point C. With the angle theta I is greater than theta C, then the light ray reflected back into the same medium and strike the core cladding interface at a point D. With angle of incidence greater than critical angle, that is theta I is greater than theta C, again it undergoes total internal reflection. This action continues at different points like E, F, and so on. In this process, the light ray propagate from one end of optical fiber to the other end without loss of energy. So the light ray travels from one end to another end with the total internal reflection without losing any energy. This is the working principle of optical fiber. You can see the light ray travels from one end to another end due to the total internal reflection without losing any energy. So, this is the principle of total internal reflection. So, the innermost region, this innermost region is core. Innermost region, this is core. The outermost, this is the core is surrounded by another region that is cladding. The light ray enters into the core medium. It is getting the incident angle is greater than critical angle. It gets total internal reflection and travel from one end to another end due to the phenomena of total internal reflection without losing any energy. This is the working of optical fiber. Working of optical fiber. Okay, this is the total internal reflection. So what we learned, we can see here simply to try to understand here. So we learned about what is optical fiber. An optical fiber is a cylindrical waveguide. Then you try to understand everything very simple. So optical fibers are glass or plastic or cylindrical tubes designed to guide the information carrying the light waves due to the total internal reflection from one end to another end without losing any energy. So we discussed about this one. Fiber optics is a technology in which signals are converted from electrical into optical signals, transmitted through a thin glass fiber and reconverted into electrical signals. So you clearly observed here the light rays are traveling with total internal reflection from one end to another end without losing any energy. So these optical fibers are made up of glass or plastic. These are the cylindrical tubes. These are so designed to guide the information carrying the light waves. For the proper guiding of information carrying light waves using the total internal reflection. What is the working principle of optical fiber? We learned total internal reflection. What is total internal reflection? When the incidence angle is greater than critical angle, then the incidence total light reflects into the same medium phenomena is called total internal reflection. So this total internal reflection is the working principle of optical fiber. So we discussed here three cases. I less than critical angle. I is equal to critical angle. And I greater than critical angle. I greater than critical angle is very, very important for optical fiber because of this condition is known as total internal reflection condition. When the angle of incidence is greater than the critical angle, the refracted ray again reflects into the same medium phenomena is called total internal reflection. So the working principle is total internal reflection. The total internal reflection is the working principle of optical fiber. So what are the conditions to get total internal reflection? The light ray should travel from denser to rarer medium, or the light ray should travel from core medium to cladding medium. The refractive index of denser should be greater than refractive index of rarer medium, or the refractive index of core should be greater than the refractive index of cladding. The incidence angle should be greater than critical angle. So we discussed about construction of optical fiber. Actually, the optical fibers mainly consist of six parts: core, cladding, silicon coating, buffer jacket, strength member, outer jacket. So the core, innermost region is called core. Simple, you remember it. The core is surrounded by another region is called cladding, silicon coating. The silicon coating is provided between buffer jacket and cladding. It improves the quality of transmission of light. The silicon coating improves the quality of transmission of light. Buffer jacket. Silicon coating is surrounded by buffer jacket. Buffer jacket is made up of plastic and protect the fiber cable from unnecessary things, moistures. So strength member. Buffer jacket is surrounded by strength member. It improves the strength member. It improves strength to the fiber cable, outer jacket. Finally, the fiber cable is covered by polyurethane outer jacket. Because of this arrangement, fiber cable will not be damaged during pulling, bending, stretching, and rolling through the fiber cable is made up of a glasses. Okay, you can see The light ray is moving in the core. The path of the light in the core in clearly you can observe. So optical fiber has three main parts: core, cladding, and plastic. The innermost region is called core. The core is made up of plastic or glass. The diameter is 50 micrometers. The refractive index is 1.48. Cladding. The core is surrounded by another region is called cladding. The cladding is made up of glass or plastic. The diameter of cladding 125 micrometer to 200 micrometer. The refractive index of cladding 1.46. So N1 should be greater than N2. So the light ray enters into the core medium, and travel from one end to another end. You can see here clearly. N1 should be greater than N2. 1.48 should be greater than 1.45 or 1.46. So the light ray enters into the core medium. It gets the total internal reflection and travels from one end to another end. That is the working of optical fiber. Working of optical fiber. Coming to the next topic, that is acceptance angle and numerical aperture. What is acceptance angle and what is numerical aperture? First, you try to understand incidence of maximum angle at the interface of air and core medium, for which the light ray enters into the core and propagated by the phenomena of total internal reflection. Then the incidence of maximum angle is called acceptance angle. You see here, I am taking cross-sectional optical fiber. So I am taking this is cross-sectional optical fiber. What is this? Optical axis. Optical axis. So I am taking this is the acceptance angle theta naught or theta A. Incidence of maximum angle at interface of air core medium. So this is core. Outside of optical fiber, this is air. So this is air core surface. Incidence of maximum angle theta naught. Incidence of maximum angle. Incidence of maximum angle. So incidence of maximum angle at air core interface. At the interface of air and core medium, for which the light ray enters into the core. The light ray enters into the core with refraction angle theta 1. This is also theta 1. Here 90 minus theta 1, or so here the incidence angle is greater than critical angle. It gets total internal reflection and travels from one end to another end due to the total internal reflection. So try to understand the acceptance angle. What I am giving the definition: acceptance angle. Acceptance angle. Incidence of maximum angle theta naught at the interface of air core medium, for which the light ray enters into core propagated by the phenomena of total internal reflection. Then the incidence of maximum angle is called acceptance angle. Is it clear? So try to understand the definition. The incidence of maximum angle at the interface of air core surface. This is the interface of air core surface or air core surface. Then the light ray enters into the core medium and propagate by the phenomena of total internal reflection. Then the incidence of maximum angle is called acceptance angle. Acceptance angle. Try to understand again clearly. Incidence of maximum angle at the interface of air core medium for which the light ray enters into the core and propagate by the phenomena of total internal reflection. Then the incidence of maximum angle is called acceptance angle. Acceptance angle. You can see here what is acceptance angle. Propagation of light, angle of acceptance, and numerical aperture. So, acceptance angle is the maximum angle of incidence with which the ray is sent into the fiber core, which allows the incidence light to the guided by the core. It is also called as waveguide acceptance angle or acceptance cone of angle. Okay, we will see what is acceptance cone. We will discuss later. So you see numerical aperture of an optical fiber. The light gathering capacity is called acceptance angle. Numerical aperture. What I am saying, numerical aperture. Numerical aperture represents the light gathering capacity of optical fiber, and it is given by numerical aperture is equal to sine theta naught. Sine theta naught. Numerical aperture is directly proportional to acceptance angle. So numerical aperture is equal to sine of acceptance angle. Sine of acceptance angle is also called numerical aperture, or light gathering capacity is called numerical aperture. Numerical aperture. We try to understand clearly about the acceptance angle. Acceptance angle. So let a ray of light AO entering into core at an angle of incidence theta naught with respect to fiber axis. With respect to fiber axis or optical axis, fiber axis. Then it is reflected along OB at an angle theta 1 and meet core cladding interface at critical angle of incidence theta c is equal to 90 minus theta 1. Then the refracted ray grazes along BC. BC. Already we discussed previously. For example, this is the normal, this is the surface. The light ray, let this is core medium, this is cladding medium, or this is denser, this is rarer. This is N1, this is N2. The light ray is incidence with the certain angle of critical angle, then the light ray travels along the surface, then it is 90 degrees. 90 degrees. So here the light ray enters into the core medium, it refracts into the theta 1, it is incident at point B, then it travels along the surface. So here this is refraction angle 90 degrees. Refraction angle 90 degrees. We will see here. So acceptance angle, the light ray travels along the optical fiber. So how the light ray travels in core and in core we can see acceptance angle we will discuss. Coming to the acceptance angle calculation. So we see here acceptance angle. I am writing here acceptance angle. It is represented by theta naught or theta A. What is the definition? The definition already completed. You try to understand this explanation. So I am giving this is the cross-sectional optical fiber. Cross-sectional optical fiber. To try to draw this one, it is very easy. So this is optical axis or fiber axis. Optical axis. So the light ray AB is incident at air core medium with the maximum incidence angle theta naught. Maximum incidence angle theta naught. Then the light ray enters into the core medium with refraction angle theta 1. This is also theta 1. So here we can observe this is 90 minus theta 1. 90 minus theta 1. So let us consider a cross-sectional optical fiber. Let n naught. So this is n naught is the n naught is the air refractive index. Air refractive index. So this is core refractive index n1. This is cladding refractive index n2. Let n0 is the refractive index of air, n1 is the refractive index of core, and n2 is the refractive index of cladding, such that so n1 should be greater than n2 should be greater than n1. No, this is air refractive index n0. So you imagine for core medium in general, this is 1.48. The refractive index of cladding in general 1.46. For air, refractive index is 1. So like that you try to remember N1 greater than N2 greater than N0. Let AB light ray is incident on the interface of air and core medium. So this is air medium, this is core medium. So this is the air core surface or air core medium. Let AB light ray is incident on the interface of air and core medium with an angle of theta naught. Then the light ray refracts into the core medium with angle of refraction theta 1. Already I wrote. The refracted light ray, this is refracted light ray BC. Refracted light ray BC is again incident on the interface of core cladding surface. This is the core cladding surface. C point is the core cladding surface or interface of core and cladding. At C with incident angle 90 minus theta 1. 90 minus theta 1. If 90 minus theta 1 incident angle 90 minus theta 1 is equal to the critical angle, What happened? Critical angle. The light ray travels along the interface of core and cladding. So at this moment, the refraction angle is equal to 90 degrees. This is the incident angle. I is equal to 90 minus theta 1 is equal to critical angle. Already we discussed previously. The light ray is incident with a particular angle theta c. The refraction angle move along the surface. Then the refraction angle is equal to 90 degrees. So incident angle is equal to 90 minus theta 1 is equal to theta c. The refraction angle is equal to 90 degrees. If the incident angle is greater than critical angle, it means 90 minus theta 1 is greater than theta c. The light ray get total internal reflection. The light ray get, if the incident angle 90 minus theta 1 is greater than critical angle, the light ray takes place total internal reflection and travels within the core and core medium. Within the core medium. So what I am saying here, you try to understand. Let us consider a cross-sectional optical fiber. Let N naught is the, you see, let N naught is the refractive index of air. N1 is the refractive index of core. N2 is the refractive index of cladding. So this is the condition. You can see here N1 greater than N2 greater than N naught. Let AB light ray, AB light ray is incident on the interface of air and core medium with an angle theta naught. Then the light ray refracts into the core medium with an angle of refraction theta 1. The refraction light ray BC again incident on the interface of core and cladding at point C with incident angle 90 minus theta 1. So if I is equal to theta C, the refraction angle is equal to 90 degrees. If I is equal to incident angle inside the core medium, I is equal to 90 minus theta 1, that is equal to theta C, then refraction angle 90 degrees because the light ray travels along the interface of core and cladding. If the incident angle 90 minus theta 1 should be greater than theta c, then the light ray reflects into the same medium phenomena is called total internal reflection. So if I is greater than theta c or 90 minus theta 1 is greater than, if I is greater than theta c or 90 minus theta 1 is greater than theta c, the light ray gets total internal reflection and travel from one end to another end. Another end. Now, coming to the definition. The incidence of maximum angle theta naught at the interface of air core medium for which the light ray enters into the core medium and propagate by the phenomena of total internal reflection, then the incidence of maximum angle is called acceptance angle. Again, definition. Incidence of maximum angle at interface of air core surface or medium and propagated by the phenomena of total internal reflection, then the incidence of maximum angle is called acceptance angle. Acceptance angle. So the light ray enters into the core medium with refraction angle theta 1. It is incident at point C. At point C, the incident angle is equal to 90 minus theta 1. If I is equal to or 90 minus theta 1 is equal to theta c, then the light ray travels along the interface of core cladding surface. Then the refraction angle is equal to 90 degrees. If the light ray incidents with incident angle I is greater than critical angle or 90 minus theta 1 is greater than critical angle, then the light ray gets total internal reflection will continue up to the second end of the optical fiber. Let us calculate the launching angle or acceptance angle theta naught. Acceptance angle theta naught. You take first at a point number 1 at a point B. I am taking all the values at point B. Incidence angle I is equal to 90 minus theta 1. Refraction angle is equal to, no, incident angle at a point. So incidence angle I is equal to theta naught. Refraction angle is equal to n naught at air. This is for air. And in cladding, N2 is equal to N1, N2 is equal to N1 and angle theta 1. So substituting all the values in Snell's law, N1 sin I is equal to N2 sin R, N2 sin R. So this is N1 is the N naught sin I is equal to, so N2 is the refractive index of core N1 into sine theta 1, sine theta 1. So from this relation, at the place of theta, at the place of I am taking theta naught because incidence angle theta naught. N naught sine theta naught is equal to N1 sine theta 1, N1 sine theta 1. From this relation, we can write sine theta naught is equal to, theta naught is equal to N1 sine theta 1 by N naught. Let this is equation number 1. Equation number 1. You can see here, if the incident angle is equal to 90 minus theta 1 is greater than critical angle, the light ray takes place total internal reflection with the core medium. Once it gets total internal reflection and traveling from one end to another end. At point B, already I discussed up to this one, n naught sine theta naught is equal to n1 by n naught sine theta 1. This is equation number 1. So you can see here at point C, at point C, the incidence angle is equal to 90 minus theta 1. Refraction angle is equal to 90 degrees. Refraction angle is equal to 90 degrees. According to Snell's law, n1 sine I is equal to n2 sine R. Substituting here n1 sine I 90 minus theta 1 is equal to sine 90 degrees. So n1, what is the sine of 90 minus theta? That is cos theta, cos theta 1. Because sine of 90 minus theta 1 is equal to cos theta 1. So this is n1 cos theta 1 is equal to, this is n2 sine 90, that is 1. So cos theta 1 is equal to n2 by n1. Let this is equation number 2. But we know that sine square theta plus cos square theta is equal to 1. So I am taking here sine square theta 1 plus cos square theta 1 is equal to 1. So sine square theta 1 is equal to 1 minus cos square theta 1. What about sine theta 1? Root of 1 minus cos square theta 1. Now substituting cos theta 1 value, sine theta 1 is equal to root of 1 minus, what about cos theta 1 from equation 2? We can write n2 by n1 whole square. So cos theta 1 is equal to n2 by n1. Cos square theta 1, that is n2 by n1 whole square. N2 by n1 whole square. So we can write this is root of 1 n1 square minus n2 square by n1 square. N1 square. So this is equal to root n1 square minus n2 square by root n1 square. This is n1. So let this is sine theta 1 is equal to root n1 square minus n2 square by n1. Let this is equation number 3. Now substituting this equation 3 in equation 1. What is equation 1? From equation 1, what is that? Sine theta naught, acceptance angle sine theta naught is equal to n1 by n naught sine theta 1. So I am substituting here n1 by n naught sine theta 1, n1 square minus n2 square by n1. So this n1 gets cancelled. We get sine theta naught is equal to root of n1 square minus n2 square by n naught. Theta naught is equal to sine inverse of root n1 square minus n2 square by n naught. That is the acceptance angle. You can see clearly here at a point C. You try to observe here at a point C. I is equal to 90 minus theta 1. So substituting in Snell's law, this is the Snell's law. N1 sin I is equal to N2 sin R. So this is as it is N1 sine of I is equal to 90 minus theta 1. I am substituting here 90 minus theta 1. Right side N2 as it is sine R. At the place of sine R, we want to take here 90 degrees. So this is sine 90 degrees. This is 1. You can see here n1 as this sine of 90 minus theta 1. This is cos theta 1. So n2 sine 90, that is 1. We can write here cos theta 1 is equal to n2 by n1. This is equation number 1. Equation number 2. We know that sine square theta plus cos square theta is equal to 1. This is sine square theta 1 plus cos square theta 1 is equal to 1. So sine square theta 1 is equal to, we can write 1 minus cos square theta 1. Sine theta 1 is equal to root of 1 minus cos square theta 1. Sine theta 1 is equal to whole root of 1 minus. I am substituting cos theta 1 value, n2 by n1. So 1 minus n2 square by n1 square. Sine theta 1 is equal to whole root of n1 square minus n2 square by n1 square. Now substituting this equation 3 in equation 1. So substituting in equation 1, from equation 1, what is that? Sine theta naught is equal to n1 by n naught cos theta 1. So substituting n1 by n naught cos theta 1 root of n1 square minus n2 square by n1. So this n1 gets cancelled. Here n1 gets cancelled. Sin theta naught is equal to root of n1 square minus n2 square by n naught. For air medium, refractive index is equal to 1. Therefore, in above equation may be written as sin theta naught is equal to root n1 square minus n2 square. So sin theta naught is equal to root of n1 square minus n2 square. Acceptance angle theta naught is equal to sin inverse of n1 square minus n2 square. This is the acceptance angle. We try to understand here clearly again. So on applying the Snell's law, At air core surface, this is the air core surface. So left side, this is air n naught, incidence angle theta naught. So this is core n1 angle theta 1. So left side air, right side I am taking core. So refractive index n naught, acceptance angle or incidence angle theta naught. So for core, refractive index n1, refraction angle theta 1. I am substituting all the values in Snell's law. Snell's law n1 sine I is equal to n2 sine r. So left side substitute at the place of n1. This is n naught sine theta naught is equal to, at the place of n2 I am taking this n1. At the place of refraction angle I am taking theta 1. So that is n naught sine theta naught n1 into sine theta 1. From this relation, we can write sine theta naught is equal to n1 by n naught sine theta 1. So that is equation number 1. Equation number 1. And applying Snell's law at point B. Here, point B. In this, here, point B. This is O, this is B. In our, this is A, this is B, this is C. Don't confusion. This is let B, this is C. So here also at point B, this is B, this is C. At point C, left side, incident angle is equal to 90 minus theta 1, refraction angle N1. For cladding, that is refraction angle 90 degrees, co refractive index n2, substituting all the values in Snell's law. N1 sine I is equal to n2 sine r. Don't confuse. N1 as this sine I 90 minus theta 1 is equal to n2 as this sine r sine 90 degrees. You can see here clearly. So this is n1 sine 90 minus theta 1 cos theta, already I discussed, that is equal to n2 into sine 90. This is what. So cos theta 1 is equal to, we can write n2 by n1. This is equation number 2. We know very well from trigonometry sine square theta 1 plus cos square theta 1 is equal to 1. So we can write sine square theta 1 is equal to 1 minus cos square theta 1. Sine theta 1 is equal to root of 1 minus cos square theta 1. So we can substitute here sine theta 1 is equal to root of 1 minus, what is cos theta 1, n2 by n1, so square, this is square. So sine theta 1 is equal to root of n2 square minus n1 square by n1 square. So we can write here, this is sine theta 1 is equal to root of n1 square minus n2 square. Root of n1 square I am taking out, that is n1. Root n1 square, that is n1. So we can write this equation like this, equation 3. Sine theta 1 is equal to 1 by n1, root n1 square minus n2 square. Substituting equation 3 in equation 1, sine theta naught is equal to n1 by n naught, 1 by n1, root of n1 square minus n2 square. So this n1 gets cancelled. Sine theta naught is equal to 1 by n naught, root of n1 square minus n2 square. Or simply, we can write sine theta naught is equal to n1 square minus n2 square by n naught. theta naught is equal to sine inverse of n1 square minus n2 square by n naught. This equation is known as acceptance angle. Acceptance angle. So coming to the acceptance cone, you see clearly acceptance cone. Rotating the acceptance angle. So this is the acceptance angle. This acceptance angle is rotating. Rotating the acceptance angle about the fiber axis, we get an incident cone with semi-vertical angle as shown theta A. This incident light cone at the core of an optical fiber will be accepted by the fiber for equidence through it and is known as acceptance cone. So you try to take here, this is the cross-sectional optical fiber, you know very well, cross-sectional optical fiber, optical axis. So this is the acceptance angle theta naught. As it is the same value of acceptance angle theta naught or theta A is rotating about the fiber axis, we get an incident cone. This is the cone. We get an incident cone. This incident cone is known as acceptance cone. Acceptance cone. Rotating the acceptance angle about the fiber axis, we get an incident cone with a semi-vertical angle theta A. This incidence cone is known as acceptance cone. What I am saying, you try to understand here. I am taking simply this is cross-sectional optical fiber, cross-sectional optical fiber. This is the optical axis. This is the incidence of maximum angle or acceptance angle. Rotating the acceptance angle about the optical axis. This is theta naught or theta A. With a semi-vertical angle as theta A. What I am saying, rotating the acceptance angle about the fiber axis, we get an incident cone with a semi-vertical angle as theta A. So in this process, we get one incident cone. That cone is known as acceptance cone. You can see here acceptance cone, acceptance cone. So numerical aperture. Coming to the next topic, numerical aperture. Numerical. So what is numerical aperture? The light gathering capacity is called numerical aperture. You can see here. So the light is incident, it is gathering here. You clearly observe here. Numerical aperture is a characteristics of any optical system. For example, photo detector, optical fiber, lenses, etc. are all optical systems. Numerical aperture is the ability of the optical system to collect all of the light incidents on it in one area. That is called the light gathering capacity is called numerical aperture. The blue cone is known as the cone of acceptance. As you can see, it is dependent on the acceptance angle of the optical fiber. Light waves within the acceptance cone can be collected in a small area which can then be sent into the optical fiber source. So this is the optical fiber core source. This is core. This light is incident with the acceptance angle and enters into the core medium. Then it is collecting all the light rays or light waves. So numerical aperture is a characteristics of any optical system. For example, photo detector, optical fiber. lenses, etc., are all optical systems. Numerical aperture is the ability of the optical system to collect all of the light incident on it in one area. The light gathering capacity is called numerical aperture. The blue cone is acceptance, cone of acceptance. The blue cone is known as the cone of acceptance. As you can see, it is dependent of the acceptance angle of the optical fiber. Light waves within the acceptance cone can be collected in a small area, which can then be sent into the optical fiber source. So the light gathering capacity is called numerical aperture. You can see here numerical aperture within the acceptance angle, the light is entering into the core medium. So it is traveling due to the total internal reflection from one end to another end. Numerical aperture shown in above figure is the measure of maximum angle at which light ray will enter and be conducted down the optical fiber. This is the numerical aperture for your understanding only. So you can see here numerical aperture, the light gathering capacity of a optical fiber is known as numerical aperture. The light gathering capacity is proportional to the acceptance angle. So, numerical aperture, the light gathering capacity means numerical aperture is directly proportional to acceptance angle. The light gathering capacity is proportional to the acceptance angle theta naught. So, numerical aperture can be represented by the sign of acceptance angle. This is numerical aperture is equal to sine of acceptance angle. So numerical aperture is equal to sine theta naught. What about sine theta naught value? Root of n1 square minus n2 square by n naught. If refractive index of air n naught is equal to 1, then numerical aperture is equal to root of n1 square minus n2 square, n2 square. So we can see here clearly. The light gathering capacity of a optical fiber is known as numerical aperture. The light gathering capacity is proportional to the acceptance angle theta naught. So numerical aperture is equal to sine theta naught. Numerical aperture is equal to root of n1 square minus n2 square by n naught. If refractive index of air medium n naught is equal to 1, then numerical aperture is equal to n1 square minus n2 square. We can calculate one problem on numerical aperture. Calculate the numerical aperture, acceptance angle and critical angle of a fiber having a core refractive index 1.50 and cladding refractive index 1.45. You can see here solution. Refractive index of core 1.5 N1, refractive index of cladding, that is N2 is equal to 1.45. We know very well numerical aperture formula, root of N1 square minus N2 square, substituting root of N1 1.5 square minus 1.45 square. You can see here. After calculation, we get 0.384. So acceptance angle also we can take theta naught is equal to sine inverse of root of n1 square minus n2 square, or simply we can write numerical aperture sine inverse of 0.384 we get 22.5 degrees. Critical angle also we can calculate here. Theta c is equal to sine inverse of n2 by n1. That is equal to sine inverse of substituting n2 1.45 by n1 1.50. So we get sine inverse of 0.966, that is equal to 75.016 degrees. This is the problem. Calculate the numerical aperture, acceptance angle, and critical angle. Three problems are there. Of a fiber having core refractive index 1.5, cladding refractive index 1.45. So first one, numerical aperture formula, you need to learn n1 square minus n2 square. Second one, acceptance angle, sine inverse of root of n1 square minus n2 square, or sine inverse of, you can write this is numerical aperture. Number three, critical angle theta c is equal to sine inverse of n2 by n1. Substituting all the values in these formulas, in three formulas, we will get the answer. So numerical aperture, this is first one. Root of n1 square minus n2 square, substituting n1, this is 1.5 whole square minus 1.45 whole square. We get numerical aperture 0.384. Second one, try to calculate acceptance angle. Acceptance angle theta naught is equal to sine inverse of numerical aperture. You can see here sine inverse of numerical aperture. Sine inverse of numerical aperture value 0.384, that is equal to 22.5 degrees. Critical angle theta c, this is third one. Critical angle theta c. Theta c is equal to sine inverse of n2 by n1. That is equal to sine inverse of 1.45 by 1.5. That is sine inverse of 1.45 by 1.5. This is 0.966. So after calculation, this is 75.016 degrees. Coming to the next problem. The angle of acceptance of an optical fiber is 30 degrees. When kept in air, find the angle of acceptance when it is in medium of refractive index 1.33. The angle of acceptance of an optical fiber is 30 degrees. You see here, this is 30 degrees, which kept in air. Find the angle of acceptance when it is in medium of refractive index 1.33. Given solution, given acceptance angle is theta naught is equal to 30 degrees. When fiber is kept in air, the refractive index n naught is equal to 1. So we know very well sine theta naught is equal to root of n1 square minus n2 square by n naught. N naught. So substituting root of n1 square minus n2 square is equal to, you write here, this is sine 30 degrees is equal to root of n1 square minus n2 square by 1. So this is 0.5 is equal to root of n1 square minus n2 square, n2 square. So we calculated the root of n1 square minus n2 square. Then acceptance angle in a medium we need to calculate here. When fiber is kept in a medium of refractive index n naught, so sine theta naught is equal to, I am taking sine theta naught dash is equal to root of n1 square minus n2 square all divided by n naught dash. So this is 0.5 by what is the n dash value? This is I am taking n naught dash 1.33. So this is 0.5 by 1.33. We get 22 degrees. Theta naught dash is equal to 22 degrees. We try to understand the problem. The angle of acceptance of an optical fiber is 30 degrees. When kept in air, find the angle of acceptance when it is in medium of refractive index. The given acceptance angle is theta naught is 30 degrees. When fiber is kept in air medium of refractive index, n naught is equal to 1. So sine theta naught is equal to root of n1 square minus n2 square by n naught, or 1 by n naught root n1 square minus n2 square. So according to this formula also, 1 by n naught, this is air refractive index 1 remaining as it is. So sine 30, this is 0.5. We calculated root of n1 square minus n2 square is equal to 0.5. Coming to the acceptance angle in medium, theta naught dash. When optical fiber is kept in medium of refractive index n naught dash is equal to 1.33 given here. So formula sin theta naught dash is equal to 1 by in medium n naught dash into root of n1 square minus n2 square. So sin theta naught is equal to 1 by n naught dash 1.33 into root of n1 square minus n2 square 0.5. So we get sin theta naught is equal to 0.5 by 1.33. Theta naught is equal to 22 degrees. 22 degrees. Coming to the next topic, fractional change in refractive index. So this is equal to I am taking root of this is n1 plus n1, n1 plus n2. I am taking as this. So n1 minus n2, that is from equation 2, we can write n1 delta, n1 delta. So I am taking here n1 delta, n1 delta. If n1 is approximately is equal to n2, n1 plus n2, we can take n1 at the place n2 also we can take n1. I am taking here root of n1, n2 is equal to also n1. So n1 plus n2 remaining n1 into delta. Root of this is 2n1, n1 plus n1, 2n1 into n1 delta. This is equal to root of 2 delta n1 square. Root n1 square outside this is n into 2 delta. So numerical aperture is equal to n1 root 2 delta. Numerical aperture can be increased by increasing refractive fractional change in refractive index delta. This enhancing the light gathering capacity of the optical fiber. Optical fiber. So numerical aperture can be increased by increasing delta, fractional change in refractive index. So what is the definition of fractional change in refractive index? So fractional change is represented by delta, that is equal to n1 minus n2 by n1. The ratio of the difference of refractive index of core and cladding. The ratio of difference in the refractive index of core and cladding to the refractive index of the core, that is called fractional change in refractive index. So delta is equal to n1 minus n2 by n1. relation between numerical aperture and fractional change in refractive index. So the relation between numerical aperture and delta. Simply, we can write from this relation n1 minus n2 is equal to n1 delta. But we know very well this is numerical aperture. Numerical aperture is equal to root of n1 square minus n2 square. So we can write this is root of a square minus b square formula. A plus b into a minus b. This is n1 square minus n2 square. So we can write n1 plus n2 into n1 minus n2. So this is equal to root of n1 plus n2 as this. So n1 minus n2 is equal to, we can substitute here n1 delta. If n1 approximately is equal to n2, so I am substituting this is n1 plus n2 is equal to n1. I am substituting n1 plus n2, remaining n1 into delta. So this is root of 2n1 into n1 delta. So we can write this is equal to n1 into root of 2 n1 square delta. Root of n1 square, we can write n1 root 2 delta. This equation is known as the relation between numerical aperture and fractional change in refractive index. The fractional change in refractive index value increases, the numerical aperture also increases. So this is another method. So we can write here this is n1 root 2 delta. Another method also we can see here root of n1 square minus n2 square. So we can write a minus b into a plus b formula. This is n1 minus n2 into n1 plus n2. We can write. So here this n1 minus n2 I am taking here as this. n1 plus n2 also I am taking here as this. So this 2 multiplying here dividing 2. So we can take 2 by 2 and also multiplying with n1 and dividing with n1. So clearly you can see here in this formula this is n1 minus n2. I am taking here as this. So this formula I am writing here root of n1 minus n2 n1 plus n2. So I am multiplying with 2, dividing with 2, and also multiplying with n1 and dividing with n1. So I am taking this is 2n1 here, 2n1. So this is n1 minus n2. I am taking here as this, divided by n1. I am taking here. So remaining n1 plus n2 I am taking here as this, divided by n I am taking here. So this is equal to root of 2n1 as this, n1 minus n2 by, we know very well, delta is equal to n1 minus n2 by n1. This n1 minus n2 by n1 I am taking here delta. This is delta. So remaining n1 plus n2 by 2 as this. So as this. I am taking here for this root of 2n1 delta as this. This is n1 plus n2. Let approximately N1 approximately is equal to N2. This is N1 as it is. At the place of N2, I am taking N1 whole divided by 2. So this 2 gets cancelled. So this is equal to root of N1 delta into N1 plus N2 to N1. So this is equal to, I am taking numerical aperture is equal to root of 2N1 square into delta. So this is equal to root N1 square, outside of that N1 root 2 delta. So delta value increases, numerical aperture value also increases. increases. So next topic, modes of what is modes of propagation? When light beam consisting infinity number of parallel light rays which are close to each other or launched at one end of the optical fiber within the acceptance angle. The rays which undergoes constructive interference will travel along certain specific directions. These directions are called as modes of propagation. Modes of propagation. What is V number? So modes of propagation and what is V number? V number, or it is also called normalized frequency. The number of modes in an optical fiber is called V number. V number. So V is equal to pi d by lambda root of n1 square minus n2 square. So we know very well numerical aperture is equal to root of n1 square minus n2 square. So at the place of root n1 square minus n2 square, I am taking here numerical aperture. So V is equal to pi d by lambda into numerical aperture. Aperture. Clearly, you try to understand here the optical fiber supports any number of rays for propagation, but it is found that it allows only a certain restricted number of rays for the propagation. The maximum number of rays or paths supported by the fiber for the propagation of light is called modes of propagation. Based on the modes of propagation, fibers are classified into single mode and multimode fibers. In a given optical fiber, the modes of propagate along the axial path is called axial ray or zero order mode. The modes of propagate at angles close to critical angle are called higher order modes. The modes propagate at angles greater than critical angle are called lower order modes. The number of modes can be evaluated with the help of V number or normalized frequency, which is given by V is equal to pi d by lambda root n1 square minus n2 square, or V is equal to pi d by lambda numerical into numerical aperture, or the V number V is equal to 2 pi by lambda into A into numerical aperture, where A is the radius of core. Lambda is the wavelength of light that propagate through the fiber or optical fiber. So V is equal to 2 pi by lambda into A, or 2 pi A by lambda into numerical aperture. So this is equal to, we can also write 2 pi by lambda A. Numerical aperture we can write n1 into root 2 delta also, where here this d we can also take d is equal to 2A or D is equal to 2R. D is equal to 2A or 2R is the diameter of the core. A or R is the radius of core. This is A or small r is the radius of core and lambda being the wavelength. So the number of modes is equal to V square by 2. V square by 2. Simply what I am saying, the modes of propagation and V number. When a light beam consisting in finite number of parallel light rays which are close to each other are launched at one end of optical fiber within the acceptance angle. The rays which undergoes constructive interference will travel along certain specific directions. These directions are called modes of propagation. So V number or normalized frequency. It is represented by V. V. The number of modes of propagations or the number of modes in an optical fiber is called V number or normalized frequency. V is equal to 2 pi A by lambda into numerical aperture or 2 pi A by lambda into N1 root 2 delta. Or another one, V is equal to pi D by lambda root of N1 square minus N2 square. So this is numerical aperture. V is equal to pi D by lambda into numerical aperture, where D is equal to 2A or 2R, that is the diameter of the core. R is the radius of core, or A is the radius of core. Lambda is the wavelength. The number of modes is equal to V square by 2. So types of optical fibers. Types of optical fibers. Types of optical fibers based on number of modes. Optical fibers are classified into two types based on the number of modes of propagation in the guide. They are single mode fiber, multimode fiber. So single mode fibers are having one mode of propagation, multi-mode fibers are having many modes of propagations. So single mode fiber, in a fiber, if only one mode is transmitted through optical fiber, then it is called single mode fiber. Multi-mode fiber. If more than one mode is transmitted through the optical fibers, then it is called multi-mode fiber. So actually, optical fibers are classified into two types. Optical fibers are classified into two types. You see clearly, I am taking here optical fibers are two types. Okay, here based on the modes of propagation, optical fibers are classified into two types. Optical fibers are classified into two types. Depending on the refractive index, refractive index, the optical fibers are classified into two types. Now I am discussing here depending on modes of propagation, depending on number of modes of propagation, the optical fibers are classified into two types. Single mode fiber and number two, multi-mode fiber. So depending on the refractive index also, the optical fibers are classified into two types. Step index fiber, graded index fiber. We will discuss later about this. Step index fiber and graded index fiber. So here, single mode fiber. In a fiber, if only single mode of propagation or one mode is transmitted through optical fiber, then it is called single mode fiber. So multimode fiber, if more than one mode or large number of modes of propagations through the optical fiber, that is called multimode optical fiber. If more than one mode is transmitted through the optical fiber, then it is called multimode optical fiber. Okay, simply we can see the differences between single mode fiber and multimode fiber. You can see single mode fiber have only one mode of propagation. Figure, you can see only one mode of propagation. Only one ray is passing through this one. In multimode fiber, have large number of modes of propagations. You can see more than two in this figure. You can observe here. So V number is less than equal to 2.405. This is the ideal V number. That is V number 2 pi A by lambda n1 root 2 delta less than or equal to 2.405. For multimode fiber, the V number 2 pi A by lambda n1 root 2 delta is greater than 2.405. Simply, we can give the differences here in single mode fiber and multimode fiber. So, we can observe single mode fiber and multimode fiber. What are the properties? What are the advantages? Okay, so single mode fiber and multimode fiber. What are the properties? Single mode fiber, only one mode can be propagated. In multimode fiber, it allows large number of modes of propagations or light to pass through it. So second point, second property, the single mode fiber has, you see clearly, the single mode fiber has a smaller core diameter and difference in refractive index of core and cladding is very small. But here you can observe it is very large. Both the core and cladding in refractive indices, difference is large as the core diameter is large. So try to understand here, first point, first property in single mode fiber. In single mode fiber, only one mode can be propagated. But in multi-mode fiber, this fiber it allows large number of modes for light to pass through it. Here, second point, the single mode fiber has a smaller core diameter and difference in refractive index of core and cladding is very small. In multimode fiber, both the core and cladding in refractive indices difference is very large. So the core diameter is also large, very large. So advantages of single mode fiber. These are the disadvantages. Okay. So advantages you can see here. Here also advantages. No dispersion. There is no degradation of signal during the propagation. The input signal match with the output signal. There is no any disturbance. So there is no any dispersion. If the input signal will not match with the output signal, it has some disturbance in output signal. The output signal overlap with each other, so we get some dispersion in the output signal. But in single mode fiber, there is no dispersion. There is no degradation of signal during the propagation. But in multimode fiber, dispersion is more due to the degradation of signal due to the multimode. Due to the multimode, the input signal will not match with the output signal. The output signal overlapping with each other. Due to this, we cannot get a perfect output signal. So it has the more dispersion in multimode fiber. In single mode fiber, you can see here, since the information transmission capacity is inversely proportional to the dispersion, the fiber can carry information to longer distances. The information can be carried to the shorter distances only. Using the multimode fiber, the information can be carried to shorter distances only. So disadvantages we can see here. Launching of light into single mode fiber and connecting two fibers are very difficulty. Launching of light into the multimode fiber and also connecting two fibers is easy in multimode fiber. The single mode fiber installation or fabrication is difficult as it is more costly. The fabrication of multimode fiber is very easy and the installation cost is very low. Very low. So try to understand here the differences between single mode fiber and multimode fiber, or distinguish between single mode and multimode fiber. So what are the properties of single mode fiber? What are the advantages? What are the disadvantages? So in single mode fiber, only one mode can be propagate through the optical fiber. In multi-mode fiber, it allows large number of modes of light to pass through it. In single mode fiber, the single mode fiber has a smaller core diameter and the difference in refractive index of core and cladding is small. In multi-mode fiber, both the core and cladding in refractive indices difference is very large as the core diameter is large. Advantages. In single mode fiber, there is no dispersion. In multimode fiber, it has the more dispersion. In single mode fiber, the information transmission capacity is inversely proportional to dispersion. The fiber can carry information to longer distances, but multimode fiber, the information can be carried to shorter distances only. Disadvantages. The launching of light into the single mode fiber and connecting two fibers are very difficulty. In multimode fiber, launching of light and also connecting two fibers is easy. In single mode fiber, installation or fabrication is difficult as it is more costly. The installation or fabrication of multimode fiber is very easy and the installation cost is also very low. So types of optical fibers based on the refractive index profile. Already I discussed it. Classification of optical fibers are two types. Depending on modes of propagation, these are two types, single mode fiber and multi-mode fiber. So types of optical fibers, depending on the refractive index profile, the optical fibers are also classified into two types on the basis of refractive index. They are step index fiber, graded index fiber. So step index fiber, you can see here, step index fiber, you can see. If the refractive index reference difference in the core and cladding varied step by step, then the fiber is called step index fiber. In step index fiber, the refractive index value is changing. So you can see if the refractive index difference in the core and cladding is varied step by step, then the fiber is called step index fiber. Graded index fiber. If refractive index difference in the core and cladding is gradually varied in a number of small decreasing index steps, then the fiber is called graded index fiber. Refractive index profile. You see here refractive index profile. If any optical fiber, the cladding has a uniform refractive index value, but the refractive index of the core may either remain constant or vary in the particular way. The curve which denotes the variation of refractive index with respect to the radial distance from the axis of the fiber is called the refractive index profile. So you can see here types of optical fibers. The optical fibers are classified under three categories. So actually only two types. Number one, step index fiber, and number two, graded index fiber. But the step index fiber, single mode, step index fiber, multimode, step index fiber, or step index single mode fiber, step index multimode fiber, and graded index multimode fiber. Simply, we can say graded index fiber also. This classification is done depending on the refractive index profile and the number of modes that the fiber can guides. So this is simply single mode fiber, only one ray you can observe. So here multi-mode, large number of modes of propagations you can observe. So this is the multi-mode graded index fiber. Just I am giving outlook figure. Now, types of optical fibers. The optical fibers are classified into three types. Already we discussed. Step index single mode fiber, step index multi-mode fiber, graded index multi-mode fiber. The classification is depending on the refractive index profile and the number of modes that the fiber can be guide. Step index single fiber, only single mode of propagation you can observe. You can observe. In step index of optical fiber, the refractive index of core remains constant throughout the core. The transmission of information will be in the form of signals or pulses. Step index fibers further classified into two types, single mode step index fiber, multi-mode step index fiber. Step index single mode fiber. You can see from this point to this point, refractive index of core N1 is constant. So you can observe clearly here step index single mode fiber. The diameter is 60 to 70 micrometer. The core diameter 8 to 10 micrometer. This is the ray propagation. A single mode step index fiber, a single mode step index fiber consists of a very fine thin core of uniform refractive index surrounded by cladding of refractive index lower than that of core. Since there is a brunt change in that refractive index of core and cladding at the interface, it is called step index fiber. Since the core size is very small, the numerical aperture is also small and hence support single mode. The accept light from laser source, they are used in submarine cables. So clearly you can see here, this is the basic structure of step index fiber as shown in this figure. This is also we know, this is the single mode. So you can observe here, this is 8 to 12 micrometer core diameter, 125 cladding diameter. It has very thin core of uniform refractive index of higher value. The core is surrounded by a cladding of uniform refractive index of lesser value than that of the core. A typical step index single mode fiber may have a core diameter of cladding 50 to 125 micrometer. A refractive index changes in step index at the core cladding boundary. So its refractive index profile takes the shape of a step. Due to its small core diameter, only a single mode of light ray transmission is possible, as shown in this figure. You can see here. So try to understand here a single mode step index fiber, a single ray input signal. You see, this is the input signal enters into the core medium and travels from one end to another end. This is the output signal. The input signal match with the input signal match with the output signal. So there is no intermodal dispersion. There is no dispersion in the signal propagation throughout the optical fiber. So if a for a single mode step index fiber, a single light ray, that is input, a single light ray, this is input, enters into the fiber and travels a single path. You see, this is the single path, and forms the output signal. In this case, two signal inputs and output signal match with each other as shown in this figure. So this is the single mode step index fiber signal propagation through the optical fiber. Characteristics of step index fiber. The characteristics of step index single mode fibers are follows. It has very small core diameter. The value of number of or numerical aperture is very small. So the core diameter is small. Numerical aperture is also very small. Simply you try to understand. It can support only one mode in which the entire light energy is concentrated. Because of less number of modes of propagation of light, the modal dispersion loss is completely reduced. There is no intermodal dispersion. It has a very high bandwidth. Single mode step index fiber has very high bandwidth. The light is passed into the signal mode fiber through laser diodes. Laser diodes. So, what are the characteristics? The step index fiber, the single mode step index fiber, diameter of core is very small. The numerical aperture is very small. So, only one mode of propagation, which the entire light energy is concentrated because of less number of modes of propagation of light. The modal dispersion loss is completely reduced in single mode step index fiber. The single mode step index fiber has very high bandwidth. The light is passed into the single mode fiber through laser diodes. Advantages. It has very high capacity. The single mode step index fiber has very high capacity. The 80 percentage of all fibers that are manufactured in the world today are of this type. What are the disadvantages? In spite of so many good qualities, the use of very thin cores creates mechanical difficulties in the manufacture and handling. Hence, this type of fiber is very expensive. What are the applications of step index fiber? The single mode step index fiber used as under C cables where the expense is justified by the high return of earned income. It finds particular applications in submarine cable system. It is used in long distance applications like telephone lines. These are the single mode step index fiber characteristics, advantages, disadvantages, and applications and use. So coming to the multi-mode step index fiber. So you can see here step index multi-mode fiber, the core diameter 50 to 200 micrometer. This is core diameter. The cladding diameter 100 to 250 micrometer. This is square type signal as input signal as used here. Input signal. The square type input signal is used. So this is another signal. Input signal. This is similar to the single mode step index fiber with the exemption that it has a larger core diameter. The core diameter is very large as compared to the single mode optical fiber. You see here, for example, this is the optical axis. Optical axis. Okay, so multimode, they accept light from both laser as well as from light emitting diode. They are used in data links. Used in data links. So multimode step index fiber, that is the transmission or propagation of light through the multimode step index fiber. So multimode step index fiber, you can see this is step index multimode fiber. So in this, the refractive index is constant. Here you can see the core diameter is 50 to 200 micrometer. So cladding diameter 125 to 400 micrometer. The geometry of the normal cross section of a typical step index multimode fiber is shown in above figure. Its core has a much larger distance, which makes it easier to support the propagation. Already we discussed the core diameter 50 to 200 micrometer and cladding diameter 125 to 300 micrometer. So refractive profile takes off a step because of larger diameter of core. The propagation of many modes within the fiber is allowed. This is explained in above figure by many different possible light rays paths through the optical fiber. So you can see here, try to understand here. So I am taking here cross sectional optical fiber. The propagation of light through the optical fiber, I want to explain here. So this is the cross sectional optical fiber. Cross sectional optical fiber. Cross sectional optical fiber. So you can see here, this is the optical axis. Optical axis. So this is the, you see here, square type input signal we are giving like this input signal. So this is the input signal. The light ray enters into the core medium with refraction angle. The light ray enters into the core medium with refraction angle. This is ray 1. With the refraction angle, you can see another ray enters into the core medium as ray 2. Ray 2. So compared to ray 1 and ray 2, ray 1 has the large refraction angle compared to ray 1. Compared to ray 1. So ray 1 gets number of incidents. You can see this is ray 1. Ray 2 gets less number of incidents and comes out first as ray 2. So you can see here in a multimode step index fiber, due to large width of core, greater number of light rays from the input signal enters into the core and takes multiple rays are passing through the optical fiber. The light ray 1, the light ray 1, which makes greater angle with the fiber axis, suffer more reflections through the fiber and takes more time to travel the optical fiber. Whereas the light ray 2 makes less angle with the axis, suffer less number of reflections, and within a short time, it travels the optical fiber at the output of second end. We received ray 2 first and later we get ray 1. Due to the path difference between the light rays, when they superimpose to form the output signals, the signals overlapped with each other. This is the output signal. The output signal overlap with each other. The output signal overlap with each other. So try to understand here. This is the optical axis. So this is ray 1. This is ray 2. Ray 2. So ray 1 enters into the core medium with greater angle refraction and ray 2 enters into the core medium less greater angle. So ray 1, what I am saying here, so first the light ray 2 makes less angle with the axis, suffer less number of refractions, and within a short time it travels the optical fiber at the output and receive ray 2 first and later we get ray 1. Due to the path difference between the light rays, when they superimpose to form the output signal, the signals are overlapped. In this, we get signal distortion known as intermodal dispersion. It is difficult to retrieve the information carried by the output signal. Output signal. So what I am saying here, try to understand here. I am giving very simple, clear. Try to understand here. This is the cross-sectional optical fiber. This is the optical axis. So we are giving square type signal here as input signal. So the light ray 1 enters into the core medium and also light ray 2 enters into the core medium. Compared to this refraction angles, you see this is high The ray 1 enters into the core medium with greater refraction angle compared to ray 2. So ray 2 gets less number of incidents and comes out as ray 2. Ray 1 gets large number of incidents and comes out later. So due to this path difference, the ray 1 comes first, ray 1 comes last. So the output signal overlapping with each other, so we get the intermodal dispersion in multimode step index fiber. So multimode step index fiber characteristics. The light can be launched into a multimode fiber using light emitted diode source. It has high core diameter. The multimode step index fiber has high core diameter. It has low bandwidth. It has high numerical aperture. The multimode step index fiber has high attenuation. So advantages. Since light emitting diode is used as a source of light, they are easier to make. Number two, they are less expensive and require less complex circuitry. They have longer lifetime than the laser diodes, thus making them more desirable in many applications. So it is the least expensive of all the fibers. Disadvantage. They suffer from intermodal dispersion loss or transmit time dispersion. Applications or uses. They are widely used in data links which require low bandwidth. Okay, graded index fiber you can see here. So graded index fiber, this is the diameter of core, this is the diameter of cladding, 100 to 250 micrometers. A multimode fiber has concentric layers of refractive index is called graded index fiber. It means the refractive index of the core varies with distance from the fiber axis. The refractive index is maximum at the center. For example, this is the optical axis. At this place, the refractive index of core is maximum. From this optical axis to cladding surface, it is decreasing from the distance. So, what I am saying here, the core varies, the refractive index of core varies with the distance from the optical axis. From the optical axis to surface, the refractive index of core N1 value decreases. The refractive index is maximum at the center and decrease with the radial distance towards to core cladding interface. In graded index fibers, the acceptance angle and numerical aperture diminish with radial distance. They accept light from both laser as well as from LED light emitting diode. They are used from medium distance communication. For example, telephone link between central offices. So graded index fiber. The geometry of the normal cross section of a typical graded index fiber is as shown in this figure. A typical graded index multimode fiber has a core diameter 50 to 200 micrometer and cladding diameter 100 to 250 micrometer. The refractive index profile is shown in above figure. The diameter of the core is high, then the intermodal dispersion loss must be high. But because of the gradual decrease in the refractive index of the core, the modal dispersion loss is minimized. Actually, there is no any disturbance in graded index fiber. So the light ray propagate for this fiber is shown in this figure also. It is also denoted by graded index fiber. So try to understand here what I am saying. Try to understand here. So I am taking again, this is cross sectional optical fiber, cross sectional optical fiber. This is axis, optical. Here we can use this type of parabolic signal we will use. The refractive index value changing from optical axis to cladding. So these are the input signals. We are sending input signals into the graded index fiber. Graded index fiber. So this is one signal. So this is another signal. Here also this is one signal and this is another signal. You can see number of signals here. Number of signals we can observe here. So transmission of signal propagation when two light rays, this is one, this is two. Light rays, one and two, making different refraction angle, making different angles with the axis, enters into the fiber, they adjust their velocities due to the varies of refractive index and come to focus at the same point. Come to focus at the same point. As a result, all light rays will be received at the output end. So, like this, these are adjusting their velocities and they are focusing at the same point. So, like this, the light rays focusing at the same point as an output signal. This is output signal. So all light rays will be received at the out end at the same time. There is no intermodal dispersion because of the input signal match with the output signal. There is no overlapping in output signal, so there is no intermodal dispersion. And the output signals match with the input signal. It is easy to receive the information from signal. In this fiber, we get a refocusing effect of light rays. So, what I am saying, try to understand here when two light rays, 1 and 2, making different refraction angles with the axis enters into the fiber, they adjust their velocities and focusing at the same point. Focusing at the same point and come to focus at the same point. As a result, all the light rays will be received at the output end at the same time. These are coming out at the end of the optical fiber at the same time. There is no intermodal dispersion because the input signal match with the output signal. There is no overlapping in output signal. So there is no intermodal dispersion. Intermodal dispersion. So here the graded index fiber V number Vg is equal to Vg is equal to 1 by 4 V square. But single mode or multi-mode step index fiber, the V number Vs is equal to 1 by 2 V square. For step index fiber V number, Vs is equal to 1 by 2 V square. For graded index fiber, that is 1 by 4 V square. Characteristics of graded index fiber. What are the characteristics of graded index fiber? The graded index fiber has an intermediate bandwidth and capacity. Compared to single mode, so the graded index fiber has intermediate bandwidth and capacity. Intermediate bandwidth and capacity. It has low attenuation. The numerical aperture value is very small. Graded index fiber has a small numerical aperture value. The source for this fiber is either a laser or light emitting diode. What are the characteristics? The graded index fiber has an intermediate bandwidth and intermediate capacity. Graded index fiber has low attenuation. The graded index fiber has a small numerical aperture. The source for this graded index fiber is either a laser source or light emitting diode source. What are the advantages? Intermodal dispersion can be reduced by using this type of fiber. It is a high quality fiber. So using the graded index fiber, we can send the signal with perfect quality to the second end. So intermodal dispersion can be reduced by using this optical fiber. In optical graded index fiber, the input signal match with the output signal. So there is no intermodal dispersion. So the intermodal dispersion completely reduced in graded index fiber. So it has high quality optical fiber. A disadvantage. It is the most expensive of all types of optical fiber compared to single mode and multi-mode optical fiber. The graded index fiber is most expensive. So next point, it is splicing could be done with some difficulty. What are the disadvantages? It is the most expensive of all types of fibers compared to single mode fiber, step index fiber, and multi-mode step index fiber. Second disadvantage, it is splicing could be done with some difficulty. What are the uses or applications? Optical fibers find their applications in the field of communication, medicine, and industry. So many applications are there for graded index optical fiber. What are the main differences between step index and graded index fiber? The difference is refractive indices is obtained in the single step and hence called single step index fiber. So this is the definition. What is the step index optical fiber? So the difference is refractive indices is obtained in the single step. Hence it is called step index fiber. For graded index fiber, due to non-uniform refractive indices, From optical axis to core cladding surface, the refractive index value is changing. So due to this non-uniform refractive indices, the difference in refraction index is obtained gradually from the center towards interface. So it is called graded index fiber. The light ray in step index fiber, you see the light ray propagation is in the form of meridional rays and it passes through the fiber axis. The light propagation in graded index fiber is in the form of skew rays and it will not cross the fiber axis. The path of light propagation in step index fiber is in zigzag manner. The path of light propagation in graded index fiber is helical, that is spiral manner. So step index fiber has lower bandwidth, graded index fiber has higher bandwidth. So graded index fiber distortion is more in multimode step index fiber. Already we explained. So in graded index fiber, the intermodal dispersion or distortion is very less, or there is no intermodal dispersion due to self-focusing effect. Due to the self-focusing effect, there is no intermodal dispersion. So V number for single mode step index fiber is equal to V square by 2. Here for graded index fiber, that is V square by 4. V square by 4. So in this video, clearly we discussed about optical fiber. Thank you one and all. Thank you so much.